Oh,
okay. So we are on YouTube live now.
Introduce me. You got to host a meeting.
yes.
So shall I start now?
Yes, go sir.
Yeah. So hello everyone. Welcome to this very special rendezvous session with Professor Harry Gray. So before proceeding for the session, I would like to have an announcement. So next Sunday at around 5 p.m. we are going to host a rendezvous session with Professor 𝗕𝗏𝗄𝗎, who's going to talk about the how mathematics impact the real world through computer simulations. So without a further ado, I would like to ask Dr. Jyothishman Das Gupta to introduce the speaker.
Okay, well, it's my pleasure. It's a great honor and pleasure to introduce one of my science heroes, Professor Harry Gray, from the California Institute of Technology, as we all call it as Caltech. So Professor Harry Gray actually is the Arnold O Beckman Professor of Chemistry at Caltech. And he has been there almost at the start of the Beckman Institute and almost from 1966. So that makes it almost 56 years of stay at Caltech. And of course, the plethora of scientific accomplishments that he has achieved over these last 50 to 60 years is something that you all can go and read about from the wonderful internet and the Wikipedia site that he has. So I do not have to repeat that part of it, but I would still like to just give a little bit of a feel for where he comes from. His undergraduate degree was from the Western Kentucky University in 1957, and his PhD was from Northwestern University, where he was part of this wonderful subgroup of inorganic chemists that ultimately, produced great inorganic chemists across states as well as in the world. He was part of this very nice group that was led by Fred Basolo and Ralph Pearson, as well as 𝗖𝗵𝗲𝘆. And I think Harry has lots of stories to talk about how that group shaped his thought process about chemistry and inorganic chemistry. But what is fundamental to Harry's sort of scientific accomplishments is his own curiosity about colors and how he actually started sort of asking this question: why are certain compounds colored and what causes them to be colored? And I think this pursuit, very fundamental pursuit, led to his discovery of electronic transitions in different kinds of metallic systems and description of them theoretically, which he worked out in his postdoctoral work, as well as his independent work in Columbia University, where he started as a principal investigator. But one of the most important contributions for Harry's entire scientific career is now captured in all the textbooks that we read about electron transfer, which is he described for the first time something he calls as the tunneling timetable, which talks about how long-range electron transfer takes place in proteins and sort of describes the structure, the internal structure of proteins. So I would not like to go too much into the details of this, but I'll let Harry speak for himself. But I would like to say that there is some personal interaction that I had with Professor Gray for all these years. Although I'm not his student, I have never been, I've never worked with, on a paper with him, but the greatest legacy of Professor Gray is he touches everybody around him with the same kind of love that he gives to his own students and postdocs. He absolutely goes to all posters in big meetings, goes to every student's poster, asks them questions, and I was a recipient of those. Also, I was recipient of very nice interactions when he visited us at Princeton when I was a graduate student with Charles Dismukes, and we hosted him for a special student-hosted seminar. Ever since, Harry, you have been very special to me and many of the students in Princeton, and we remember you fondly for that visit. And I hope these students get a chance today to really see how much you care for the scientific community and the scholarship and develop scholarship amongst young students. So Harry, without further ado, I would like to welcome you. And I do not want to mention all the awards that you won, but you have made all of us proud with just being there in chemistry. And, you've of course won all the top prizes, and I'm still expecting the biggest one someday you would win. And I would like you to come over and give us this wonderful lecture. Thank you, Harry.
Thank you, JD. It's not too late for us to publish a paper together.
Sure.
So maybe we'll do that in a few years, okay? Because I'd love to couple with you and the wonderful students in Mumbai that are going to listen to me for a while and chat with me and talk. I'm going to talk about metal oxos, and because their colors are something like the color of permanganate and colors that intrigued me as a boy. When I was 11 years old, I had potassium permanganate, and I wondered why it was this beautiful deep purple color. I made Prussian blue when I was 11 years old, and I wondered what that deep blue color in Prussian blue was due to. And so I spent most of my early life trying to figure out what these colors were due to, and I'll talk about that in the first part of my talk. To motivate the talk, I will give you my version of the top 4 chemical reactions on planet Earth. I say modestly. There's no doubt that the most important reaction on planet Earth is photosynthesis, green leaves that splits water into oxygen and makes protons and electrons to make fuels and materials. It's catalyzed by a manganese cluster in photosystem 2 in green leaves. The second most important reaction is respiration, where the oxygen that's made in photosynthesis is re-reduced in our mitochondrial respiratory system by an enzyme called cytochrome C oxidase, which contains copper and iron. It reduces it all the way to water. If it didn't reduce it all the way to water, it would be very, very bad, because it would make very toxic radical materials, so-called reactive oxygen species, but it doesn't do that. It goes all the way to water. My third choice is in chemical reactions is nitrogen fixation, where nitrogen is reduced in bacteria and other organisms by an enzyme called nitrogenase, which has iron and molybdenum in it. It's called 𝗕𝗏. Reduces it to ammonia. Of course, the process that makes most of the ammonia that we use for fertilizer is the Haber-Bosch process, which has an iron catalyst. My fourth choice is alkane oxidation in our bodies with an enzyme called Cytochrome P450 that we'll talk about in this talk. That takes hydrocarbons and soluble ones and oxidizes them to alcohols so they can be used in the body to make important molecules for life. Now, what motivates my talk is that of these 4 reactions, which are the most important ones on the planet, 3 of them have metal oxos as key intermediates. And so metal oxos, multiply bonded metal oxos, are really important molecules and species which we should understand their electronic structures. And I'll give you the 3 key ones here in this slide. In water oxidation to dioxygen, which of course JD knows all about because he worked with Chuck Dismukes. You know all about this, JD. You could give this talk. On the left is one of the proposed intermediates. It's not the only one. There are several proposals. But one proposal is that there's a manganese 5 triple bond oxo intermediate in this system of this cluster of 4 manganeses and a calcium. In the center is the known intermediate in cytochrome oxidase in respiration, and that's an iron 4 porphyrin double bond oxo. And on the right is the known intermediate in cytochrome P450 called compound 1, which is a double bond iron oxo with a radical porphyrin, which has a little density on the sulfur. The thing that intrigued me so much and motivated a lot of my work is that the chemistry of these three oxos is so incredibly different. On the left side, the triple bond oxos have never ever been protonated. Their so-called pKs are like -20. No one has ever protonated a triple bond oxo, so they have no proton affinity. But if you go to the double bond oxos, they have lots of proton affinity. The one in the middle has a pK of about 3 to 4. And the one on the right, once it's reduced to compound 2, is a strong base. The oxo in compound 2 of P450 has a pK of 12 to 13. It's a strong base, and that's why it works. These proton affinities span 30 pK units. So why is that? So I'm going to tell you why. That's why I went to Copenhagen in 1960 from Northwestern, as JD has pointed out. And I must say I was really annoyed when I went to Copenhagen, because the physicist had invented a theory called crystal field theory. And crystal field theory, invented by the physicists, had taken all the bonds away from all my nice compounds. And these physicists could explain a few colors, but not any of the ones I was interested in. Permanganate, for example, they couldn't explain. They couldn't explain the vanadiylline, which you see in this picture. So I went to Copenhagen and I told my boss there, Carl Ballhausen, that I was going to invent a new theory that would put the bonds back into my molecules and also explain the colors of all compounds, because there were so-called DD transitions, which the crystal field could explain a few of, but not all. There were charge transfer and intervalence transitions, which the physicists couldn't explain at all. So I went to Copenhagen to develop a new theory, which is now called the ligand field theory, if you've ever heard of it. This first ligand field calculation is shown here in this slide on the right. What I showed was there's a very, very strong triple bond between the oxygen and the vanadium in that left diagram with a distance of 1.67 angstroms. The oxygen that's very close to the vanadium is a triple bond according to my ligand field theory, because there's a doubly degenerate bonding level called 𝗕𝗵𝗲 bonding. There's a non-bonding level called B2 where you put an electron. And there's a very strong pi anti-bonding level, which is called 𝗕𝗵𝗲. My theory showed that the anti-bonding level in metal oxos is very energetic, and you can't put very many electrons in it to have a stable structure. So you end up with this system being a triple. So I proposed this was a triple bond for the first time, and I explained the beautiful blue color of the vanadiylline for the first time. The physicists had completely screwed it up, but I got it right. And as you can see, though, there's no triple bond in this diagram, and that's because my boss, Carl Ballhausen, was a little nervous. He was a crystal field type guy, and he didn't want to put any bonds in. And I said, Carl, that's a triple bond. And he said, I'm not so sure. I said, no, Carl, it's a triple bond. He said, well, Harry, if you think it's a triple bond, write your own paper. And I said, I've already written it. Because I did all the work. I did all the theory. I did all the experiments. I wrote the paper, and he put his name on it. And I said, well, I've got another paper ready, and I'm sending it in right now with a triple bond in there, and I did. And the next issue of Inorganic Chemistry is the first time a triple bond oxo has ever been or triple bond of any kind of a metal ligand has ever been listed. And then my diagram on the right again shows the pi star level very high. So what this did was to show that you could put a total of 4 d electrons into a multiply bonded oxo, but that's it. You put in 1, 2, it's a triple bond, then you put in 1 in pi star, it's a 2.5, then you put 2 electrons in pi star, it's a double bond triplet state, just like dioxygen. But you can't put any more in pi star because the system will collapse at that point. So this is what this criterion of you can only put 4 d electrons into a metal oxo set up this famous oxo wall that I proposed for the periodic table. I said, you cannot go with a metal oxo, you cannot go past the iron, ruthenium, osmium triad in the periodic table. So I made the proposal that there's an oxo wall between iron, ruthenium, and osmium, and cobalt, rhodium, and iridium, and I dared anybody to give me a tetragonal oxo or a tetrahedral oxo beyond that wall. And I proposed that 50 years ago, and 50 years later, no one has crossed my wall with a tetragonal. In fact, a few years ago, I offered a huge reward, a huge prize for anybody who gets a crystal structure, and I'll offer that to all of you in Mumbai. If you can send me a crystal structure of a multiply bonded oxo across my wall, I will give you the prize. But to date, no one has done it. In fact, the metal oxos in biology are all on the correct side of the wall. The manganese 3 triple bond oxo, manganese 5 triple bond oxo on the left. Then the ligand field theory shows that if you reduce the manganese triple bond oxo to a double bond oxo, manganese 4, because of the atomic physics of the electron-electron interaction, you now get a high spin state from a low spin state, making it a double bond oxo. And the pK from the triple bond oxo to the double bond, the pK change is 20 units. So this biology uses this to do chemistry. Then on the right is the 𝗲𝗏𝗆 ion, the famous 𝗲𝗏𝗆 ion, which is the intermediate in all sorts of biological reactions, including cytochrome P450. So Mike Green and John Dawson and I published a paper in Science explaining how P450 works. On the left, you see a hydrocarbon coming up to the active site of P450, which is a strong oxidant. Compound 1 is a strong oxidant, over a volt oxidizing. And an electron is ripped off of the CH bond and then generating this very basic oxo, which grabs the proton. So if that oxo weren't very basic, this cytochrome P450 would never work. It would never be able to actually activate this. Then, as JD knows, there's a guy at Princeton named Jay Groves who proposed this mechanism like 50 years ago, and we have basically shown that Jay Groves' mechanism, this so-called rebound to give the alcohol from this 𝗬𝗿𝘆 dot is actually it's right. But
Jay doesn't put the triple bond, I think. There's sometimes in his papers it's a double bonded manganese 5. So that's something.
This this double bond to going to this 1.5 is the way this goes because of the number of electrons, JD. But at this point, I figured I understood this in 2004, so I lost interest in this. Once figured this out, and then I got very interested in something that Jay Groves worried about 50 years ago, and that is, why don't we just oxidatively degrade? How can we live with enzymes that operate with these metal oxos that are powerful oxidants? They're so powerful oxidants, they should in fact oxidize all the proteins they're in before they oxidize the substrates. And so I got very interested in how we can live as long as we do, because if these highly oxidizing oxos were not protected somehow, our livers and our spleens, our cells would be destroyed in a few minutes. And when you were born, you wouldn't live to be over 4 days old if these oxos weren't protected somehow. And so I started thinking about this. Jay Winkler and I started thinking about it, and in 2014, I made a proposal. Here you see the Cytochrome P450 enzymatic cycle. The upper cycle is the one that works, that makes alcohols. The lower one is the so-called uncoupling one, where the substrate's not there. And if it weren't protected somehow, it would destroy our cells and destroy our bodies, and you'd die. You'd die within the few minutes of this talk if we weren't protected. In fact, the most important human enzyme is only 10%, as you can see in the upper part, is only 10% efficient. 90% of the time it goes on this lower uncoupled path. So how are we protected? Well, I made the proposal that we're protected by tryptophan, by the amino acid tryptophan down there. You can see it, TRIP. What I proposed was, without any evidence at all, is that tryptophan, which is an amino acid that came in with the great oxygen burst billions of years ago, tryptophan, I proposed that there would be a tryptophan sitting about 7 angstroms to 10 angstroms from the active site. It had to be a little further away, because if it was right at the active site, it would reduce the thing, so you'd never get any turnover. I proposed it would have to be 7 to 12 angstroms from the active site, and if the substrate weren't there, it would transfer an electron directly into the highly oxidizing compound 1 and compound 2 to protect it, to move it back over. And I published a paper with Jay Winkler in the Philosophical Transactions. I went to London. I'm a foreign member of the Royal Society, the famous Royal Society, a bunch of Englishmen in 3-piece suits who talk funny. And I went to the Royal Society and I gave this talk, which I said, I'm going to speculate on this tryptophan. I said, this is wild speculation. Of course, the British, being very proper, refused to say it was wild speculation. When they published this in the Philosophical Transactions, they called it an opinion piece. The good old British. I'm very glad we beat them in the Revolutionary War, because they're very annoying. Anyway, so I proposed this. So Jay Winkler and I wrote a big, actually Jay wrote a big code so we could interrogate the protein data bank, all 100,000 structures, to see if there were tryptophans close to the active sites of all these enzymes. And sure enough, there are. There are tryptophans in every one of them that are 7 to 12 angstroms from the active site. Not only that, there are tyrosines that are coupled with them, chains, tyrosine tryptophan chains that go from the active site to the surface. Here's one. This is a very famous, very important human P450. It's called CYP11A1. It does steroid biosynthesis. It's the substrate's cholesterol. You can see it there in green, but right after the green, you can see those tryptophans, and then tyrosines all the way out to the surface. So as JD said, I've spent half my life studying electron tunneling through proteins. So I can, for my tunneling timetables, I can calculate exactly how fast that tryptophan and chain will tunnel an electron into that heme to protect it if the substrate's not there. And we call those hopping maps that are based on my tunneling timetables. So I calculated how fast that these tryptophans at 9.6 and 12.6 angstroms would tunnel an electron into the compound 1 if the substrate weren't there. And it turns out to be half of a microsecond, which is 500 nanoseconds. So basically that tryptophan is telling that active site heme, OXO, look, active site heme, if you don't if you don't do your work, and if you don't hydroxylate that substrate, I'm going to protect you in 500 I'm giving you 500 nanoseconds to do something. And if you don't do it in 500 nanoseconds, I'm going to protect you by kicking an electron out. And then it runs out to the oxidizing out to the tyrosines at the surface, where they can be reduced by cellular reductants, like ascorbic acid. This interested a whole bunch of theoreticians now have jumped into this with very high level calculations to check my tunneling timetable stuff. David Baratan at Duke did it with this. He checked mine out, and it checks out with a very fancy calculation. And they published a paper calling it diffusing redox bombs, which is really what this is. So we now have an enormous amount of evidence that our bodies are now protected by these tryptophan tyrosine chains that are in these enzymes in all of you. And now there's been lots of experimental evidence that's come out. So this looks like it may be right. But now I'm going to finish my talk, because I see I wanted to talk about 25 minutes. I want to finish up so we can have a good conversation about everything, and you can ask me all kinds of questions, including what am I good for? Let me go back to probably the most important reactions that metal oxos do, and that's photosynthesis. Because metal oxos are involved in the splitting of water to oxygen, which is my #1 reaction. This is done as I told you, in this manganese calcium cluster that JD knows all about. And this is one of the mechanisms that was proposed. It was proposed by now championed by 𝗕𝗓𝗄𝗃 at Yale, but there's a German-Swedish mechanism that's different. Never mind, we do know that multi-metals are involved and calcium is involved. So it's very likely that the best catalyst for water oxidation hasn't been found yet. So there's a big search for it, and my group has worked on it. Our theory is that it's going to contain several metals. It's going to be a multi-metal system. You would say, well, why don't you just take this active site out of photosystem 2 and let that work? But what we know from bioinorganic chemistry is when we take the active sites out of proteins, they don't work anymore. They only work inside the proteins. They're tuned up. So we have to do something else. So my group invented, Jay Winkler and I and some other folks in my group invented a pulse laser plasma method to make multi-metal oxo catalyst. Here's the way it works. We take a pulse laser, triple YAG, 355 nanometer pulse laser, and put a metal powder in water, and we put metal nitrates in solution with it. If we want to make multi-metals, we blow this metal up into a plasma. And the initial temperature is about 60 to 70,000 Kelvin. It's pretty hot. By the time we can measure the temperature, it's around 10,000 Kelvin. And the plasma is then confined at very high pressure, and the shock wave forms, and we make nanoparticles whose sizes we can make by varying the laser pulse energy and the pulse width. So we have complete control in this pulse laser method of making nanoparticle catalysts, and we can make mixed metal ones. And the ones that we've made that are extremely active catalysts are iron nickel catalysts, which we make by using an iron target and hit the pulse laser and blow that up into a plasma and have nickel nitrate in solution at 3 molar nickel nitrate. And then the nanoparticle incorporates the iron and the nickel. We can also put titanium in and lanthanum. We can make any kind of multi-metal metal oxo catalyst by this pulse laser method. And then we can put the catalyst, like the one you see on the left, we can put it in acetonitrile where there's no water. So we can get the oxidation states, and iron 3 can go to iron 4 and iron 5 and iron 6. We can then do in situ IR to see what the iron 6 is. And guess what? It's a cis-dioxo. If it weren't an oxo, I wouldn't be giving this talk. It's a cis-dioxo, and it has a very clear infrared pattern of a cis-dioxo. So we know what it is. We know it's active because we put a drop of water on this solution and it makes oxygen and bleaches again. Then we can pump it back with anotically to generate it back. We go back and forth and back and forth. So we know this iron 6 dioxo is the active intermediate. We've done Musbauer to show that. We've done near infrared emission. So this is our mechanism. Our mechanism, which we published in J.O.U.L., is a cis-dioxo iron. You can see at the left up, it's a cis-dioxo. It then internally converts to a iron 4 side bonded peroxo, which we also have a vibrational spectrum of. And in our paper in J.O.U.L., our mechanism is so complicated that this famous guy, 𝗕𝗏𝗆 in Germany, had to write a paper explaining it to us. So he wrote a paper later explaining our mechanism to us on the right and showing how it matches JD with the famous S states in photosynthesis. So we start with iron 3, we go to iron 4, iron 5, iron 6 dioxo, another electron out to side bonded peroxo, another one out to oxygen and off. So our cis dioxo is the same as the S4 state, famous S4 state in photosynthesis. So we're in pretty good shape now. This is a very robust catalyst. We've got a really great pulse laser method to make these materials. So now we've added another possible mechanism in the middle there.
Professor Gray, can I interrupt? Actually, I didn't understand the experiments that you showed in the last 2 slides.
Okay.
So how did you find the experiment before this?
How did I do this?
The slide before this?
This one. How did we do
yes,
this?
So
we put this on an electrode. We sweep anotically to a couple of volts down there, polarized at 2.3 volts versus silver in acetonitrile. That generates the highly oxidized iron on the electrode. We take that. We have an in situ infrared spectrometer that measures the spectrum that you see on the right there, which gives us the fingerprint of a cis dioxo metal, which we've got many examples of. Then we put a drop of water on the electrode and oxygen comes out, which shows it's active, and it goes back up it bleaches back up. Then we polarize it to 2 volts again, generating the spectrum again of the cis dioxo. Once we do that, we put another drop of water on. It's an acetonitrile. We put another dropper on. It oxidizes that water to go back and forth and back and forth and back and forth. So by that, we show that the cis dioxo is the active intermediate. Does that help you? Think about it. My advice to you is read this paper.
Yeah, okay.
My advice is read our paper in J.O.U.L. and read this paper by 𝗕𝗏𝗆. Maybe better read the paper by 𝗕𝗏𝗆 and Chem. And
okay.
You'll see how this mechanism works, okay?
Okay.
And so now we've added this central mechanism to the upper one, which is the Yale mechanism for water oxidation, and the lower one is the binuclear German Swedish mechanism. No one has ever calculated, JD, no one's ever calculated our mechanism for photosynthesis. See if that has a chance, but I'd like to see that now. So on this last slide of mine, last technical slide, I want to emphasize what the global impact of this work is. It's enormous. Because if we can split water, if we can make electrodes, cathodes for hydrogen evolution and cathodes for nitrogen reduction to ammonia. And we can make anodes for water oxidation and methane to methanol. If we can make those electrodes, we can make custom electrolyzers that we can wire to very efficient solar arrays to drive these reactions: water to hydrogen, methane to methanol and ethylene, CO2 to ethylene, and fuels and materials, and nitrogen to ammonia. We can replace the Haber process with a solar-driven process that will use hydrogen directly rather than splitting it off from methane to pollute the planet. So my prediction is that in very near future, and we have some of these already now in California, we're going to have these PV electrolyzers using very efficient, very cheap solar arrays to drive electrode reactions at custom anodes and cathodes. And what you're seeing here is what I believe the future of this planet is, to replace oil, gas, and coal with solar-driven electrolyzers that are custom for any reaction that you want to run. So this is my group. Thanks to them, the Beckman Institute, NIH, NSF. I've had continuous NSF funding for over 60 years. I was in NSF when Sputnik went up in 1957. NSF got a lot of money and gave me a fellowship to go to Northwestern. They also gave me a fellowship to go to Copenhagen to get rid of the crystal field theory, to invent the Ligand field theory. And as soon as I got to Columbia, they called me up and said they want to continue funding my group. I didn't even apply for in those days, you could get a grant by a phone call from a director who said they wanted to fund my work. So I'm very indebted to all of these folks in my group. And so that's my story today. Thank you so much for your attention. And now I hope we can have a great discussion about anything you want to talk about.
Thank you, Harry. I would like everybody to unmute themselves and just give a big round of applause to Professor Gray. Unfortunately, this is something that is missing in the Zoom session, a physical presence, an audio of the claps that sometimes resonates across an auditorium. So thank you. Thank you, Harry.
Thank you. I think I need to stop sharing my screen.
There will be some questions, I guess.
Okay.
Yeah. So if students want to ask questions, I have one or two, but if I'll just ensure that everybody gets a chance. I think Anushka had raised her hand in the middle of the session.
I'm gonna stop sharing my screen so I can see you.
Sure, we'll do that.
Okay, now let's see. I need to get the view. Let's see.
Right, can you see us?
Let's see. I need to. I can see you now.
Okay.
Yeah, I can see you big time. Yeah. So I guess let's see if I can.
Sure. So any questions?
Okay. Now I can see you now. I got rid of my screen.
Okay.
Can you see me? Can you see me? Also?
Yes. Absolutely. Perfect.
Okay. Let's talk for a while.
Yeah. Sure. So any questions from the students?
Sir.
Yeah. Arun. Yeah.
Tryptophan is an essential amino acid.
Yes.
Arun, let me see your video.
Yes.
There you are.
Yes.
Okay. Hi, Arun. How are you?
I'm fine.
Good. You look very happy.
Yes.
What's your question?
Tryptophan is an essential amino acid.
Tryptophan is an amino acid
which is essential. Which we should take inside, which the body cannot produce on its own.
Yeah, well, tryptophan tryptophan is not a very abundant amino acid. It's but it is in everything, and Actually, turkeys have a lot of tryptophan. So if you eat a lot of turkey, you'll get plenty of tryptophan. But you don't. You have plenty of tryptophan in your bodies now, and because we found tryptophan in all these enzymes that use oxygen, so you don't have to worry. You've got it built in already.
Is there any proven the fact that persons not consuming more tryptophan have loss of cells?
I don't think taking tryptophan it might help you because it might get incorporated more into these enzymes. But I think basically your metabolic system takes care of all that. So I don't think you need a tryptophan supplement. You're okay. Don't worry.
Any other question?
I thought we were going to talk about my
yes,
my pack.
yes, of course. I think John.
Yes, I have a question. Yes, so I still I still don't understand how, if these amino acids are covering the enzyme, I still don't understand how they come out of this covering and like do what they're supposed to do, like
You don't understand. Tell me a little bit more. I'm having a hard time understanding what you're saying.
Okay, so as you had shown that these amino acids cover the enzymes and prevent unnecessary oxidation, right?
Yeah, right. They're reducing by electron transfer, because tryptophan is a very good electron transfer agent. And the important thing about it, it has the reduction potential that's tuned in very closely to the potential you need to reduce these kinds of hemes. So that's around 1 volt or so. It's one of the few, it's the only amino acid that has the right reduction potential for this. Tyrosine is a problem, because if it were close by, when it reduces a highly oxidized system, the proton flies off usually, and it won't sustain the thing very further. So of all the amino, the reason I picked tryptophan when I was looking for things that would protect, tryptophan is the only amino acid that has the electron transfer properties that are correct to put an electron into an oxidized heme at the right potential, and also have the ability to oxidize a tyrosine in the chain next to it. It's the only one that has the right properties. That's you're probably wondering how in the world I came up with this idea of tryptophan. But it wasn't just blind luck. I looked at all the redox properties of all the amino acids, and it's the only one that has the right potential to do this job.
Cool. So Harry,
maybe that helps.
No, I just wanted to yes, completely beautifully put. I just wanted to add that actually people are discovering more and more tryptophan's role in other kinds of systems as well. For example, in some of the systems that we have been working on the azurin system, if you just shine light and you know where the color comes from, the LMCT transition for the copper, the copper one, type 1.
Yeah, I know a lot about blue copper.
Right, absolutely. So you excite the system with red color, and something that we have worked on is showing that actually the LMCT transitions are more delocalized than you ever thought. Actually, it involves a tryptophan almost 10 angstroms away to initially oxidize that, and then the whole recombines again back and recombines at the copper site. So it's a very interesting process where within a picosecond you see that whole travel to the tryptophan, and then come back. So this is something that we're putting it together, but it's amazing that tryptophans are existing in proteins that take care of all these charges that you would create by even photoexcitations, just simple photoexcitations in broad daylight. So
that's exactly right. Tryptophan is a very important redox center in all sorts of proteins, not only for protection, but as you say, also for function.
Right.
For example, there's lignin peroxidase. Is a heme protein with a tryptophan at the surface, and that tryptophan is the active site for lignin degradation. So there are tryptophans that are oxidized that actually oxidize substrates.
Right.
So you're exactly right, JD. There's a huge role for tryptophan in redox bioinorganic chemistry.
Right. And there's a question from.
So the bottom line is, all you students, you better start learning about tryptophan. read everything you can about tryptophan, because it's all over the place and it's very, very important. And interestingly enough, it really started, evolution really started making tryptophan when the big oxygen burst came in, when we needed an oxygen environment, we needed tryptophan to live.
Right. Absolutely.
Because oxygen is very toxic.
Absolutely.
We can't do without it, but it's hard to work with it because it's what kills us in the long run. It's what causes aging and death. And
right.
So you've got to read all about tryptophan. It's incredibly important. So my message is, you spend the next 2 weeks studying tryptophan.
Right.
And if you have any questions for me, send me an email.
Nice. It's a W, right? It's a win-win situation.
It's a win-win. That's right. Okay.
Right. So there is a question from YouTube. One of the students is asking: is there a possibility to get over the oxo wall through an excited state process?
Yes. In fact, you can get over the oxo wall if you go over the oxo wall, you can get oxos that you can't isolate because they're very reactive intermediates and excited states and things like that. So the answer is yes. You can get over the oxo wall in excited states and radical intermediates. And
yes.
So, for example, in copper oxidation reactions, there are oxos that are radical type oxos in reactions. There are cobalt radical oxos in water oxidation. So the answer to your question, whoever that was, is a resounding yes, you can, but you cannot crystallize and isolate the ground states of these.
Right. That's
Rahul.
Because that's Rahul.
That's what you'll have to do to get my prize.
Yeah, that's Rahul Gera, who is actually asking the question, is one of my former students. So Rahul has also asked, how close is technology to achieve water oxidation efficiently? How close is the technology?
It's very close. It's already being done. It's in electrolyzers now. In California, we have solar-driven water splitters oxidizing water and making hydrogen for fuel. We have hydrogen filling stations in California now that are using the technology that I showed you. It is here right now, okay? Right. And it's just a question of politicians having the will to ramp up now, because we have the technology now to do solar to fuels and solar to materials.
Sure.
And so the answer is, it's here right now. We have very efficient oxidation catalysts.
And then there is a question by Joydeep Mondal from YouTube. Is there any possibility of having a metal tetrabond oxygen formation?
That what?
Metal tetrabond. So that means you have 4 bonds between a metal and oxo.
Oh, 4 bonds.
Yes.
No, that violates all of my rules.
Right.
if you
quadruple bonding. Yeah.
If you can get a quadruply bonded metal oxo, I will give you a big prize.
Well, you have quadruple metal binding. That's been shown.
If you get a quadruple metal oxo bond, I will send you 1 million rupees.
Yeah. Okay, there's a question from Gur Sahib, I think.
It's actually from me.
Yeah.
So
okay.
So I was asking that you mentioned that there were all these people who followed crystal field theory. So someone who does not know, so I don't know what crystal field theory and ligand field theory, the difference between them. So why do you say the bonds were all taken away from your molecule? And
yeah,
why
well,
did you have to put
in the crystal field theory, you have only one atom, a central metal atom, and you put the crystal field as point charges, say an octahedral complex, say nickel-𝗿𝗄 complex, which is green. Water, nickel +2 in water is green. It's got so-called crystal field absorption bands. In crystal field theory, you replace all the bonds and all the atoms with point charges and point dipoles. So you would replace the water molecule with a point dipole. And so you would have 6 point dipoles in an octahedral arrangement, 6 to make an octahedron. And so the crystal field theory would have the nickel-𝗿𝗄 complex as a central nickel +2 metal ion with 6 dipoles at the corners of an octahedron. That's what nickel-𝗿𝗄. There'd be no bonds between the water. There'd be no waters. There'd be nothing except the nickel 2 and point dipole. So something like iron, something like hexafluoro iron 3 with 6 fluorides in an octahedral complex. They would replace the fluorides with point charges. So there'd be no bonds. All the molecules and ligands would be replaced by either point charges or point dipoles. That's the crystal field model.
So how does it create a problem for you to show the triple bond of oxygen in crystal field?
There's just the electrostatic interaction between the dipole or there are no bonds. There are no bonds in the crystal field theory. The point is they're just electrostatic interactions. In the crystal field theory, the electrostatic interactions split the levels of the d levels, but there aren't any other levels, so you can't explain any charge transfer transitions or anything that had to do with ligand electrons. The ligand electrons aren't there. So in permanganate, for example, tetrahedral permanganate, they have 4 point charges in a tetrahedral arrangement. There are no oxygen electrons to make a transition. There are no bonds.
Okay.
It's ridiculous. It's completely ridiculous. It's absurd. It should have been thrown out a long time ago.
Does it have to do with those diagrams, the energy splitting diagram?
If you read my Vanadil paper, the one I showed, if you read that paper, see that I showed that the crystal field theory with electrostatic interactions cannot explain anything about the Vanadil line. First of all, in my paper, I showed that it was ridiculous. And then I invented a new theory, which the details I haven't given you because I figured what I did was I found a way to, if you want the technical parts, I found a way to calculate the diagonal elements of energy. I used the atomic physics to do the electron-electron interactions. I put together an MO theory along with electron-electron interactions to put together so that you could put the bonds back in and also split the levels. It's interesting that if you do a very elaborate crystal field calculation, you don't even get the right splittings.
Okay.
So crystal field theory is just terrible.
I have a question in the same line, is that how were you so confident about your theory? like even your PI was questioning it, and you still wanted to publish it. So how you got so much
Well,
that
my
motivation?
theory accounted for a lot of things for a long time, but my theory could not calculate accurately the ground state structures. And so after, as usual, after about 40 years, my theory has been replaced by something called DFT and TD-DFT. So now you'll see most of the calculations for the last 20 years. But my theory was good from about the 60s and 70s to the mid 80s. And then now it's been superseded. So as usual, theories come and go. And my model has been replaced now with what's called DFT. You may have heard of DFT and TD-DFT. No, I'm not confident. I knew it would be replaced. It doesn't do everything, but it did give a qualitative and semi-quantitative model to explain the colors of all, pretty much all compounds. It was used, for example, by a guy at Bell Labs to explain the color of Prussian blue. It will do intervalence, but quantitatively to get structures, to get bond links and things like that, my theory is terrible. And so it eventually was replaced, as I knew it would be. So the answer is, I know, and you should understand this as well. Whatever you do now is likely to be replaced by something better. So my advice to you is don't get confident about that you've got the last word about anything. And also, if you make a mistake, admit it immediately, and say, okay, I made a mistake. That experiment of mine is wrong, or that theory of mine is wrong, and go on to something better. The mistake a lot of people make is exactly what you just asked me. They get so confident that they're right, so right, that even if the experiments start showing that they're probably not right, they keep holding on to the hope that it is right, rather than admit it's wrong. For example, if you work for some professor who's famous or something, and you find out something that professor said is wrong, you tell him that. Or if you do an experiment that's wrong, you tell them that. Now, don't. The most important thing is to science is to not be totally confident about what you do, that you will keep trying to protect it. And when you know it's wrong, the most important thing you do is admit it. You say, well, I made a mistake. I'm wrong. There's going to be a better model, a better theory, and I'm probably going to work on it. So your question to me is a really important one. How confident I am? Well, when I invented this, I knew there would be something better that would come along. It took a few years, but when it came along, well, that's what I do now. I do DFT and TD. I don't do my theory anymore. I do better theories, okay? And so that's my message to you.
That was nice.
Okay, great. Well, that was a great question. It allowed me to talk about something that I'm really interested in, because I'll tell you one thing, fraud in science comes about because people who try to hold on to something that's wrong too long because they're afraid to admit they're wrong. And what this does is young people then work hard to show that the professor is right when they know the professor is wrong. And when you know the professor is wrong, you better tell the professor you're wrong, because otherwise you'll start cheating and making up stuff and spiking your samples with something that gives the right NMR and stuff like that. And that's most science fraud comes about because students don't tell the professor that the professor is wrong. So when JD is wrong, you tell him, you say, JD, you're wrong.
Yes.
Yeah, I'll do that.
Yeah.
And the important thing is that my students, I've been wrong hundreds of times, okay? Almost all the mechanisms that I proposed initially have turned out to be wrong. Because if you're out there in front and you're proposing mechanisms of reactions, the chances your first mechanism is right is very, very slim. It's almost certainly not right, because you're making a proposal, and my chains, which I propose, they're probably not going to end up being right. Somebody's going to correct them somehow. And they're not right in detail. I'm sure that somebody will come along and figure out something better. So when that happens, I better admit it. I say, well, I screwed up again. So that's my message to you. Don't be scared to be wrong, because if you're wrong and you admit it, it probably leads to something even better, because the next step will be better than the last one. So it will free you from all of this stuff. Anyway, I've talked enough on this. Let's go to something else.
Thank you, Harry. This was very nice. Any other question?
I wanted to add something. So so when you proposed your theory, the CFT theory was one of the more popular ones out there. So is it surprising that it got accepted, or your theory got published in the very next issue of the journal, as you said? Because usually we don't see people accepting new ideas which come along, right?
Well, that's a problem nowadays. That's a problem that's plaguing us in science nowadays, that people are reluctant to accept new things. But when I started, inorganic chemistry, when I started, was just beginning to gain momentum. You see, when I went to school, inorganic chemistry wasn't even a field. What we called inorganic chemistry, they weren't in the inorganic chemists. JD pointed out that one of the few inorganic chemists was Fred Basolo at Northwestern University. When I was in school, there were no courses in inorganic chemistry in undergraduates. The courses in chemistry were physical chemistry, organic chemistry, and analytical chemistry. That was it. There was a little bit of inorganic and introductory chemistry, but there were no separate courses in inorganic chemistry at most schools in the United States, most big universities. 2 or 3 had inorganic. Northwestern was one of the few universities that actually had modern work going on in inorganic chemistry, because before the 1960s, inorganic chemistry was devoted to discussing the manufacture of sulfuric acid and all those wonderfully boring subjects. And so now I'll give credit to the physicists who invented crystal field theory, because they did change our whole ideas. Even though it turned out to be wrong, they re-energized the field by showing that there was actually some theory that would explain some colors of some compounds. And so crystal field theory was really responsible for getting people into inorganic chemistry in the 1950s, okay? And so there were only a few of us in the field, and the journal started in 1962. The journal Inorganic Chemistry started, and the journal was looking for new ideas. They were really looking for new ideas. And so I was asked to send my first papers. The editor of the journal was Bob Perry, and he asked me to send these new ideas to the journal to publish. So it was very different then. The field was just taking off. And so to give you an example of this, I got a professor's job at Columbia University without an interview. I had never been to Columbia University. I was in Copenhagen developing my theory, and I'd never been at Columbia. I didn't have a CV. I didn't apply for a job there. one day they knew about my work on this new theory. They knew about it. And one day I got a letter in Copenhagen from the chairman of the department of Columbia University offering me a job, offering me a assistant professorship. I had never been there. I didn't send them an application. I didn't have a CV. I didn't have any proposals. I was just developing this. Those were the days when this field was really taking off in all directions, in spectroscopy, in photochemistry, in something called I just talked about bioinorganic chemistry. It took off. Organometallic chemistry started. Solid state chemistry started. All of these fields started in the late 50s and early 60s. And so there were really no courses in the field. There were only 4 or 5 young people like myself doing work in the field. And so in order for young students to have any training in this field, the National Science Foundation started a summer program at Reed College in Portland, Oregon, and asked a few of us who were in the field to come out to Portland, Oregon for the summer and teach this modern inorganic chemistry they just started. And kids came from all schools from all over the country where there weren't any inorganic courses, and they took this summer course. And a lot of the inorganic chemists who went into the field were in these NSF summer courses in the 60s. So the bottom line is, in answer to your question, people were looking for new ideas in inorganic chemistry in the early 60s, and they were welcoming them, and they were publishing papers right and left. You could send anything in and get it published in the early 60s in this field. So does that answer your question? Where'd you go? There you are.
Good. I'm good.
I lost him.
I
lost you. I want to see your face. I want to see if I answered your question.
Yes, sir. My video is on. If you can see me, 𝗕𝗫𝗫𝗫.
I can see you now.
Yeah.
You look terrific. You look very happy. You look like a very happy guy. Bring him back. I want to talk to him. Bring him back. Where did this guy go? There you are. You're 𝗕𝗫𝗫𝗫𝗫.
Yes, sir. 𝗕𝗫𝗫𝗫𝗫.
𝗕𝗫𝗫𝗫𝗫. I've heard of that's a famous name.
Yes, sir.
You know that. That's a very famous name. So what do you do? Tell me about yourself.
So I am currently in my 4th year in CBS in Mumbai, and I am majoring in physics. Physics.
So you're very unhappy with me, but but I gave you full. But it was the physics theory, it was the crystal field theory that really re-energized this field. It's a so-called renaissance of inorganic chemistry. Came about because of the physics people getting in, showing us some stuff that we could get started on. And so what is your work? What are you working on in physics?
So,
are you doing research?
So not yet. So most of it is still courses. It's still coursework that we have going right now.
Have you taken any chemistry?
No, I haven't. So
you haven't taken any chemistry?
So once when I was
I want you to read some of my papers.
So sure. I'm gonna read about the tryptophan that you talked about today. That was really good. That was
read some of my papers back in ligand field theory.
Yes. No, I remember. So when I was,
you'll be converted. You'll become a chemist.
So I don't mind at all. I don't mind. I don't mind.
I want to recruit a few. I want to recruit a few bright physics people like you to go in, because we need you guys in our field in chemistry.
So I'll be more than happy.
They don't need you in physics. We need you in chemistry. So change the field.
Definitely.
So tell me, where are you in school? Now I know you. JD's at the Tata Institute, but you people must be from some universities.
Yeah, we are from
Yes.
CBS.
Are there courses at the Tata Institute?
No, so most of the students over here are from CEBS. It's an institute situated in University of Mumbai. So
The University of Mumbai.
yeah. So
it's called Center for Excellence in Basic Sciences.
Yeah.
So
I've had many Indian students in my group over the years. My first Indian student was P.T. Manoharan.
Yeah.
You
Yes.
probably heard of him. He passed away recently,
Right.
but
Right.
he was the vice chancellor
Chancellor of the University
of
University of Madras, I think.
University
Madras.
of Madras, and he was also the head of. He was a very fantastic student of mine at Columbia. One of my very first students. He worked on the ligand field theory of nitroprusside ion, which is FeCN5NO2-, where it took a while to understand the electronic structure of it, but we called him PT because his name is impossible to pronounce for me.
Yes.
There are about 16 syllables in his first name. So
Yeah.
I could only call him PT.
Right. So I
I'm
just, Harry,
getting scared.
And actually, Dr. Dasgupta, you know that the fellow I've worked with in the last 10 years is 𝗕𝗏𝗏.
aha, okay.
Who's now a really brilliant guy, 𝗕𝗏𝗏. I don't know if you have met him.
No, I haven't.
I worked with him for the last 10 years. He is now making a lot of money. He's now the assistant to the president of Amgen, a big company.
Oh, fantastic. Oh, great.
So he wasn't making a lot of money with me, but now he's making a lot.
Yeah. So Harry, I just want to point out one individual who has raised the hand. It's our student from TIFR, Department of Chemical Sciences, working with Shyamlava Majumdar, Mohammad Tahir. Tahir, could you unmute and ask question, please?
Yeah, thank you, JD, for giving this opportunity. Yeah, actually, I have the question that earlier you said in the P450 catalytic cycle that alkane oxidation is only 10% and the rest 90% is dealt with this tryptophan oxidation. So do we have some experimental evidence or can we design some experiment where we can see that rest 90% part is being taken care by this tryptophan oxidation? Or
yes,
is it?
Yes, that's a great question. The experiments we're doing now to see if tryptophan is rescuing these systems is we're replacing tryptophan with phenylalanine in mutagenesis experiments because phenylalanine can't reduce the active center. So what we're doing now is we're running turnovers with various P450s and other enzymes, copper enzymes as well. Multi-copper oxidases like lactases also have tryptophans at active sites. And we're replacing those tryptophans with phenylalanines and finding that the enzymes destroy themselves pretty quickly if they don't have tryptophan there. And so we have a couple of experiments going on now with P450s, replacing these chains redox inactive amino acids. And we've got mixed results, so it's not so clear how this is all coming out in the end. But there's a researcher in Montreal, Anne English, who's been working with heme enzymes, and she's been replacing tryptophans and so forth and she's finding good, strong experimental evidence that the tryptophans are protecting her heme enzymes. We're in the process of this now, and so what we're actually finding is that there's more than one chain. These enzymes are super protected. We found only one chain initially, but when we knocked out one of the chains by changing tryptophan to phenylalanine, we looked at it, it was still running. The enzyme was still going, and we then found 4 more chains out from other sides of the enzyme. So these enzymes apparently are really very protected. So if one chain gets knocked out by some mutation that occurs, it's still got other chains to protect it. So, so with this being the case, it's going to be really hard to knock these things out because they're super protected, it looks like. But those are the kinds of experiments that are going. To answer your question, we're changing tryptophan to phenylalanine.
Okay.
Good, very good question. Basically, your question is, you've got this cockamamie theory. Is there any evidence for it? The honest answer is it's going to be very, very difficult to really nail this experimentally because of this redundancy that seems to be now the case. Nature decided they better super protect these things because if you knock out one chain, it's still protected.
Yeah. So can we do one more thing here, that if we introduce more tryptophan nearer to the active site, so
yes. We're now with the fancy techniques in gene therapy and so forth, and with CRISPR and so on that are coming into play, where you can put in stuff like this. It's not beyond the realm of impossibility. It's conceivable now that we could actually put in tryptophan into some cells and enzymes and so forth now to protect people more. So that's a long-term thing that may be possible.
okay.
Okay, guys. Now questions that surround some of the personal experiences, Harry, that you have had. I encourage undergrads to ask these questions now, because Sanskruti, do you have a question?
Yeah, I do have a question.
Yeah.
I saw you before. You came on. I saw you, and then you disappeared.
I turned my video off.
Tell me, let's see, who are you? Let's see, let's see, you've got it here. You're
Sanskruti?
Yeah. I'm trying to read it on without my reading glasses. Yeah, well, tell us, how do you pronounce your name?
Sanskruti.
Oh, that's a beautiful name. That's a gorgeous name, Sanskruti. I wish I had a name like that. That's nice. Are you an undergraduate?
Yes, I'm majoring in maths.
In math?
Yes.
No, that's good. That's very good. We need good mathematicians. My wife was a professor in mathematics. So I'm married to a mathematician. You can look her up. She is. My wife has been championing women mathematicians. My wife was able to get the Italian government to issue a postage stamp in honor of the famous woman mathematician, Sister Maria Agnesi, on her 300th anniversary of her birthday. So the Italian government is now honoring women mathematicians. Okay. So what do you like? What would you like to know about me?
I actually wanted to know if you consciously put in effort to stay healthy.
Am I making efforts to stay healthy?
Yes, because you're quite old now, and
yeah, I'm 85 years old.
Yeah, but you're still going to lab at 6 a.m. So.
Yeah, well, that's what's keeping me healthy. I exercise every day. I'm trying to eat healthy foods. I'm trying to resist eating hamburgers every day. I drink red wine and eat dark chocolate. Dark chocolate, my theory is if you eat dark chocolate and drink 2 glasses of red wine every day, you can live to be 127 years old. Because it protects you from reactive oxygen species.
I eat dark chocolates almost every other day. So
Yeah,
thanks,
well,
Harry.
JD, you're going to live to be 127. Yeah, so the answer is I try to stay healthy, but in fact, I think it is true that if you love what you do and you keep working on it and don't retire, you stay healthier than most people, because people who stop working and they're not interested in anything tend to get Alzheimer's and things like that. And people who are, my mind is very active and I work on things every day and I'm still inventing stupid new things. And so I think you live longer if you are extremely active, both intellectually and physically. So I'll try to stay around for another couple of years.
Thank you, Sanskrit. That was a nice question. There is one question. There's one question by 𝗤𝗍𝗄𝗆. Avni, you are here. Could you ask the question?
I saw the question in the chat. It was about have I ever faced dead ends?
Right. That is from Naman.
Yes, Avni is here in the call.
Was that the question?
That was by Naman. I wanted to know whether you faced any dead ends in your long scientific career.
I would say I faced about, I would estimate maybe about 631 dead ends. Yes, essentially every week in my scientific life, you get to a dead end in which you have to start over. If you don't come up with any dead ends, you're probably not doing anything. If you're not making mistakes, you're also not doing anything. Something has happened to my screen. You still hear me?
Yes, sir. We can hear you.
Yes. Yeah. Something happened to me. I got a blank screen there for a minute, but now you're back. Okay. My favorite physics student just came back.
He never left.
I figure by the time this thing is over, 𝗕𝗿𝗄𝗆 will be a chemist. I'm not going off until you see the light. But by the way, in physics, they're nothing but everything's a dead end in physics. Have you heard about the new particle stuff? Apparently, the standard model is taking a hit now.
Only last week the new results.
Physics is just one big dead end.
Oh my God. This is going to be on YouTube for a long time, Harry. Just
this is going to be on YouTube for a long time.
They're going to quote you from here.
Okay, all right. That's right, though. That's right. We're going to have this whole section on YouTube. That's great. What else we got? We got anything else?
So yeah, there is one question: are there any possibilities of utilizing cyanide ligands into similar reactions to put it into similar use, like cyanoligands?
Yeah, well, you can use cyanide ligands for lots of things. Prussian blue is a big metal cyanide complex, intervalence iron cyanide complex, which is not only a blue pigment for paints, the famous paintings by Van Gogh used Prussian blue in his famous painting called Starry Night. And also now it's a treatment for Prussian blues now being used as a treatment for thallium poisoning. Because Prussian blue is kind of has a lot of holes in it that you can introduce monopositive metals like thallium-1. It soaks up a lot of thallium. So if you have thallium poison, you should take about 2 or 3 grams of Prussian blue every day. It's full of cyanide, but it's not toxic. You can, the cyanides are completely, encapsulated in this nanostructure. Well, cyanides there are a lot of cyanides that are in use in various contexts. So cyanide is a very important ligand for a lot of things. Right now, my research group, we're boronating cyanides, putting boron and the nitrogen in so we can use them in non-redox flow batteries to tune their redox potentials. Cyanide complexes are rare. Ferrocyanide, 𝗕𝗏𝗏cyanide are very useful redox reagents. Cyanide complexes are ubiquitous in inorganic chemistry and in applications of all kinds. Who asked that question?
This is Avni. Avni, she is in the YouTube. So unfortunately, you can't see her, as well as she's in the Zoom, but her Zoom thing is not working very well. So
this whole thing is live on YouTube?
Yes, it is.
I should have remembered that before.
It's fine.
If this gets out to the physics people, they're gonna. I'm gonna get a lot of hate mail. I hope they heard the last part when I gave them credit for starting inorganic chemistry. Right,
absolutely.
No, but then I feel even as a physicist as well, I feel that they've always had a sense of, I don't know, a false superiority among with respect to the other disciplines, right? I mean when I don't know, it was Rutherford who said all of science is either physics or stamp collecting or something like that.
He famously won the Nobel Prize in chemistry, though, Rutherford.
Yeah, for stamp collecting.
Yeah.
Yeah, well, that was
that was a disaster.
In fact, many physicists claim that there's nothing left to be discovered in chemistry. It was all laid out by physicists in the 1920s, and so it's nothing but the applications of the Schrödinger equation. and so I've had some interactions with physicists who claim there's all of chemistry is understood. There's nothing really left fundamental to discover. So I think I've tried to take that on, but I usually lose all of my arguments with physicists.
Okay. Harry, I have a question, as a personal question to you. How do you view the entire tenure system, and especially with the new, so little number of jobs available and so many excellent candidates, and you give a job and then you have this 5 years or 6 years to sort of perform. How do you view it in the context of what the current situation is about employment, about how to find another job, another place if you don't get tenure? What is going on in the mind of the person who is looking at this system, that academics has this system, and as a young scholar, I'm looking into opportunities of getting employed in a university for a faculty position, but I have to go through this process, and I see that not everybody is successful. So how do you talk to people? How do you sort of motivate people to know that this is a good system, or this has its flaws, or how do you sort of prepare yourself?
Well, the tenure system, which operated well, I think, in the old days, is probably outdated now, but I think it puts too much pressure on young people to do things that maybe they really wouldn't do if there weren't a tenure system. They feel a lot of pressure to publish too rapidly and things like that. But I don't know what, I must say I don't know anything better. So I think most people would say, well, the tenure system's probably flawed, very flawed now and out of date and should be replaced, but I don't know what to replace it with. So we're in a difficult situation now because it does put much more pressure on young people than it did when I started, because there were, at least in my field, there were jobs to go to if you didn't get tenure. Now, now if you don't get tenure, it's really hard to move to some other place. But I don't have any good ideas of what to replace it with. Do you, JD?
No, I think we have in the in few universities, including the Tata Institute, we have the tenure system in place for last maybe close to 10 years. So it's an adventure for us in India at this point. Of course, in the US, this has been going on for some time now. So
I see the tenure system is relatively new in India.
Yes, yes. It's
even
relatively
in universities.
In universities, we don't directly have a tenure system yet. So one of the things that we are bothered about is how to sort of ensure that you give protection to the new faculty. When you hire somebody, you have to sort of protect the faculty in some way so that the faculty gets a chance to explore whatever they want to do, but also have a sense of, I guess, a sense of a timing, which is hard in India simply because things don't move in India at the same pace, because it's still not infrastructurally developed. Every place in India is not infrastructurally as developed as in the United States. So implementing the tenure system in India is slightly harder. As you know, it takes time for setting up labs here, lab spaces. It takes time to sort of get your consumables to be bought in, the equipments to be bought in. Things are much more difficult in terms of the timing of it. So it's slightly becoming complicated as to how to implement it in Indian context. But I don't know if you had ideas, because you're in Caltech for this long, you've seen so many fantastic professors come and establish their labs. Some of them may not have, but what do you tell your postdocs, especially your postdocs who are looking for jobs? How do you sort of bring this into context?
Well, I must say I'm not very good at this, although my people who've gone through my group have done very well out in this system, in the tenure system. I think most have gotten tenure when they've gone out. Maybe it's because of my style of mentoring, which gives my students a lot of freedom to explore what they want to explore. I'm not very heavy-handed, so, but people who are mentors who basically direct their groups essentially every day or every hour and tell them what to do, those folks who go out, I think, don't do so well because they haven't had as much freedom as grad students and postdocs. At Caltech, we emphasize writing research proposals and things like that, and exploring new things yourself. So our people have done pretty well out in the system because of the way we operate our graduate program. There's another thing about tenure, and that is when the other side of it is some people get tenure and then they really stop working and stop doing things. And so it's one of the downsides of a tenure system is people who really should retire don't retire because they have tenure. So it's both getting tenure and then after tenure dealing with that. So there are a lot of things that are wrong in the tenure system, a lot of things that need to be corrected, but no one has come up with
A better plan, a better plan, a better plan.
No one has come up, as far as I know, with a better plan. You can, some schools, like I think Yale and Hopkins, I'm not sure about this, but I think they let you have longer, like 10 years, to promote people to positions that are maybe associate professors, and then you have another few years or something, so they let people have more time. Maybe that's one solution, is to give people more time so they don't feel under so much pressure. But I must admit, I don't have a solution to this problem, but it is a problem because it is true. I see it with our young people here. They feel really stressed before tenure to get out, and I don't know what to do about that. So I failed at another one of my failures is I haven't come up with a solution to the problem with the tenure system. So
right,
and I don't think I can. I don't think I can solve that problem.
You got other things. You got other things to solve.
I got a lot of other things to worry about. So
right.
Maybe in India, since you don't have it at universities, you will come up with a better system, and you can teach us all. You can teach us all what we should be doing. There's a lot of exciting work going on in India. There are a lot of super bright people in India, and I'm expecting you to come up with the. I'm asking you now, JD, to come up with this answer.
Sure. We're trying.
And share it with your friends in the United States. And we'll change our system if you come up with. Maybe you can do it at the 𝗤𝗏 Institute. Maybe the 𝗤𝗏 Institute can come up with some replacement for tenure that works for everybody.
Right. Okay, Harry. More questions, Guru Sahib?
Yeah, so I have a question actually. So Professor Harry, I have almost read your interview. So there is 2 different interviews of yours, 2001 and 2016 interviews. So when I was reading your interview, I got to know that your life is almost perfect. Like everything was like extraordinary.
My life is almost perfect? You got to be kidding me.
Yeah, seriously, I got that feeling while reading it because like
my life. I've had a lot of fun in my life.
Yes, it was visible through those interviews.
I've had fun everywhere I've gone. I've had so much fun doing science that's probably why I'm still alive. Is I've made science fun. It's fun to me. I love it. I really love science.
Yeah. So how was you so sure?
But I wouldn't say my life. I wouldn't say my life has been perfect. I've made a lot of mistakes.
So that wasn't visible through your interview. So I can't tell that.
Well, I'm glad somebody is listening to my interviews.
Yeah.
We all follow you, Harry. We all follow what you say. Okay.
Yeah. So really. So I had a question from that interview. Like you were so sure about that you are going to be in science. How was that surety in you that you are going to be in science since 11 years of age? You were so sure.
I can't explain that. I loved colors. I love fiddling around.
Yeah.
I love fiddling around with chemicals. I wasn't particularly interested in explosions, or things that most chemists say that they got interested in chemistry because of explosions, or they say their high school chemistry teacher had motivated them. But in my high school, there weren't any chemistry teachers. I taught my high school chemistry class when I was a student. So if you ask me who motivated me, I say, yeah, it was my high school teacher. That was me. The answer is, I can't explain it, except one of my uncles was really a very curious individual and loved nature and things like that. but somehow I got very interested in chemistry. Just I can't explain it because nobody in my family had gone into chemistry.
So actually, I'm asking this because we never taught anybody in that age. We were not sure about anything when we were in that age.
Yeah.
And
well,
you were not only good in science, you were good in other things as well.
You know, it's true that I love to mix chemicals and make different colors. And I loved reactions of all kinds. And I just built my own chemistry lab when I was a kid. And I just started reading all about chemistry. I like to get books, find books about chemistry. And so I can't explain what it was in me that drove me into the field. But I knew when I was 11 years old that I wanted to be a chemist.
But you were good in so many other things.
I haven't changed my mind. In 74 years later, I haven't changed my mind. So I can't explain this to you.
So you were very good in distributing newspapers as well. You loved it. So,
I just loved it. Yeah, I loved it. I just knew, some of my relatives passed away through dreadful diseases, and I felt that there must be some way to go into science to do something about this. And so a little bit of that, of seeing dreadful diseases take lives was one factor. But the main factor was I just loved to fiddle around with chemicals. I thought chemicals were cool. And I found when I was a kid, I found a place in Chicago that I could order big bottles of sulfuric acid and nitric acid and hydrochloric acid. And the little sets weren't enough for me. I like to get big bottles of chemicals and acids and stuff to play around with. And
even they thought that you were a professor.
You wouldn't be able to do that now. There are too many safety rules. You wouldn't be able to do what I did now.
Okay.
But I wish I could explain why I went into chemistry, but it was just somehow built into my DNA.
how chemical an answer? Okay, so, biological maybe. So Abhigyan has a question. Abhigyan, please ask your question.
Professor Gray, that was a very fantastic talk. Something that I'm very inclined to ask you is, how do you see the role industry playing in funding and taking forward basic science and fundamental research? Because in the modern day world, the Bell Labs of the days of yore don't exist anymore. And one can say the dew point of today isn't the dew point that Wallace Carothers ran and all. So what role do you see industries taking out in the modern and the future days?
Well, that's a great question. And I think industry has to take a big role in funding chemistry now, because we rely on fundamental discoveries and fundamental work to generate the capital, the intellectual capital that we need to make applications. We can't just do applied work without having a lot of fundamental work be the foundation for it. So industry should be investing in enormous amounts of money into fundamental science. And of course, DuPont did that in the old days. Bell Labs did that. Those things have stopped, but Dow, for example, invests a lot of money into fundamental research now. And the oil companies now know that they're going to have to transition to being solar energy companies and things like that in the future. The oil companies now are starting to invest much more in fundamental research. BP, for example, invested into my solar energy program 20 years ago and got me started in once again into that. So industry has to play a huge role now along with the government in making investments in fundamental research. And if industry does not do that, we will be in bad shape for the future. So, and I think industry understands that now. And also in the United States, we have a very good situation that the very rich people are investing in research. The Gates Foundation, the Beckman Foundation, the Moore Foundation, all these super rich people have set up foundations to fund fundamental research. So if you look at all the very rich people giving back and setting up foundations, you look at industries and you look at the government, those three areas need to invest enormous amounts of money into fundamental research, and I think that's going to happen. I don't know about India and how fundamental research is funded in India, but in the United States, it's going to be a partnership among government, industry, and foundations that are set up by extremely rich people. Okay.
Yeah, thank you for the.
So the short answer to this question is industry has to play a huge role in this if we're to succeed.
Thank you.
Okay. A question from I guess Chef. Sir, how was your life as an undergraduate in your era?
It was a lot of fun. I didn't come from a very well-to-do family. We made it okay, but I worked all through my undergraduate years. I worked about 60 to 80 hours a week at a newspaper. I became the person who kept all the books and did all the calculations for the local newspaper. So I made my way through undergraduate school by working. I also played Division I athletics. So I was an athlete. And so the courses weren't that hard for me, actually, because I was quite a good student. So I spent Sundays studying because I didn't have time during the week to study, but I spent Sundays studying for all my courses. And I had a great time as an undergraduate. It was a lot of fun. I met a lot of great people, made a lot of friends, met my wife. What can I say? Undergraduate, you should really enjoy what you're doing now, because as a student in undergrad and as a grad student, as a postdoc, I had the most fun ever in my life.
And you also interviewed Elvis Presley.
Everything was a lot of fun for me.
So I was saying that you also interviewed Elvis Presley during your undergrad time, I think.
Elvis.
That's right. Yeah, from the newspaper. Yes, Elvis Presley was starting to become a big star in the South. He hadn't been a national star yet, but he traveled around. He drove his car from, even at that time, he had a big following of people who traveled with him. And so there were 7 or 8 big Cadillac cars that traveled around from Memphis to Louisville, Memphis, Tennessee to Louisville, Kentucky. And they came through the town where I was an undergraduate called Bowling Green, Kentucky. And there was a big restaurant he always stopped at called Manhattan Towers. And so, as I told you, when I was an undergraduate, I worked at the newspaper. After school, I always went down to the newspaper and kept the books. And so I was the only person at the newspaper in the evening. And so Elvis Presley showed up at this, it was his entourage showed up at this Manhattan Towers place, and one of the editors of the paper found out about it, and he called me down at the, because I was the only guy down at the newspaper. He called me and he says, "Harry, go get out to Manhattan Towers and interview Elvis Presley for the newspaper." And so I drove out to Manhattan Towers and worked my way through the crowd. He was surrounded by 100 people, and I worked my way out to him, and I said, "Mr. Presley, I'd like to interview for my paper, the Park City Daily News." He says, "Okay, great." He said, "Come on out to my car." So we sat in his Cadillac for an hour where we talked, and he was, I guess at the time, about 18. I might have been 17 or 18, something like that, 18 or 19, teenagers. He's a year older than I was. So we talked for an hour, and I wrote it up for the paper, and it got published on the front page next day of the newspaper, the Park City Daily News. Yeah, I became famous for interviewing Elvis Presley before
Tunneling timetable.
before he became super famous.
Right.
It turns out he was a very, very nice guy. Even then, he told me that he could see life was getting away from him because he was becoming famous. And he says, "I fear that I'm not going to be able to control my life," he said, "because I can see it getting away from me." And that was very prophetic. Even when he was that young, that it did get away from him. As you know, he died, he did drugs, he did a lot of drugs and so forth, and didn't live that long, but he was unbelievably famous. But I had this little hour with him. And so maybe that's the most famous thing. Everybody says, "Well, Harry, you're a good chemist," but
come on,
Harry. But the only thing you ever did that was worth anything is you spent an hour with.
Oh, come on, Harry. You're such a blessing to us. So, any more questions? Okay.
We probably covered a lot of ground, haven't we, JD?
Yes, I think it's already up to 2 hours, so maybe we'll just.
Oh, that's right. We've done almost 2 hours.
Yeah.
And
Yeah.
Time went pretty fast. It's time for you guys to go to bed.
No, we are fine. We are fine.
Yeah,
Absolutely fine.
We are just afraid that you are tired or not.
How many times in the entire life do we get a chance like this, right? So we're enjoying.
I'll have to say that I've really enjoyed this interaction with all of you. Seem so exciting and so much fun and doing such great things that I'm sure you're all going to be great scientists and make this world a better place. So I'm very pleased that we had this chance to interact for a couple of hours.
Yeah, yeah. John has a question, maybe the last one, John, then we can conclude.
So in your career, you probably have had a lot of setbacks as well. So did you ever feel unsure, like you had no control of what was happening at any point in your life?
What's the question? What is the question?
So like, were you ever, were you ever unsure of what you were doing? Like you might have had setbacks and like you were not sure that you were good enough to do this, and thoughts like this.
Yeah, I can tell it this way. When I had no idea I would end up the way I did when I started when I went to Northwestern as a graduate student. I felt that if I got a good education there, I could probably become a high school chemistry teacher. My original goal was, and so you might say I was unsure of myself, of what I could actually do and whether I'd be any good at anything. So I was already, even though I love chemistry, I was unsure of how far I could go initially. So when I went to Northwestern to do graduate work, I felt that if I got a good education in chemistry there, I could become a high school teacher and go back to Kentucky, my home state, and become a high school teacher. Then I really started research with Fred Basolo, as JD pointed out, and I found that I was pretty good at it, and I enjoyed it a lot, and so my confidence grew as time went on. And when I related my ambition to be a high school teacher to Basolo and Fred Basolo and Ralph Pearson, they said, "Well, Harry, you know, I think you should go on and research, and later you can go back to Kentucky and become a high school teacher." And so they actually were the ones who urged me to become more sure of myself. And by the time I got to Copenhagen, I was quite sure of myself. So sure of myself that I wanted to take on the physics community and do that. So I have to say that I sort of evolved from an unsure person about a career into a person. I got more and more confident as I went along, and I learned more and so forth. So I hope that answers your question about how. And then when I got to Columbia and I had some success in Copenhagen, I became quite sure of myself in terms of working on things. And so I guess it came as I did research and found that I could actually do it and contribute. But coming from a background in Southern Kentucky, from farming families and things like that, you don't know what the world is like. And so I grew very, very rapidly when I went to Northwestern and got into research in organic chemistry. And so I would say my being sure of myself came rapidly as I did research and learned that I could actually contribute. And since that time, I've, of course, off and on, you know, when you do things and you get into some dead ends, you get a little unsure of yourself. So there's a bumpy road here and there, but then you come back and forth. And so it's been that kind of roller coaster, but pretty much most of the time I've been pretty sure I could contribute. I hope that.
Yes, it does answer.
Yes, thank you. Thank you, Harry. 𝗲𝗏𝘆, you want to ask the question?
So it would be nice if you can stay for long, like for some more time. But if you are tired, we can conclude the session, like, because we are enjoying it a lot.
They don't want to, you know, they want to stay for more time. But I know, Harry, you have other commitments. But are you feeling tired now? Is that something that you're feeling?
No, I'm completely energized.
Okay.
But let's do another 5 minutes or so.
Okay. Yeah, please.
Because that last question was a really important one about
yes.
About confidence and how you gain confidence.
Sure.
You gain confidence by working and doing things, and it doesn't come all at once. It comes with actually, that's why it's so important when you start working that you work on some things that are pretty easy to start with, some simple things. So you can gain confidence by working on maybe problems that aren't that big a deal, but you can solve them. You need to gain confidence in the laboratory by doing things that actually work for a while. So it's a big mistake to start on really fancy big time problems. But yet, I think if you start on just rather simple reactions that give products, and you can get crystals and stuff and feel like you can do lab work, even though it's may not be the most important thing in the world. In fact, it may be fairly boring, but if you can show that you can actually do anything, it helps your confidence.
Yes.
The lab. A mistake a lot of kids make is they try to do too much too early, and try to say, well, I'm going to work on the most important problem in the world, and I'm going to make the world's best catalyst. And so they start on things that are too difficult to begin with. Instead, they ought to be maybe crystallizing salt, sodium chloride, or something something that's been done a million times, and you know it works. So you get in the lab and you actually get something that works, and that's, I think you need to build confidence in laboratory work in order to move forward. And so don't try to do too much too fast. Don't try to solve the world's most important problem on the first day you're in the lab. Crystallize something that has been crystallized a zillion times before. And you'll see this crystal and you say, gee, I can actually do something. So that's what happened with me. I was able to work on problems that weren't all that big a deal to begin with, but you could do them and you could get confidence. And my confidence built over the first 2 or 3 years in doing experiments that I could do that worked. And then I could take on bigger, as I grew older and more experienced, I could take on bigger and bigger problems as far as the world was concerned.
Yeah. Okay, Harry. There's a question by Avni. How big a role does money play in any researcher's career? In what ways can it hold you back or empower you?
Well, money is, of course, very important if you want to do research and buy chemicals and get instruments and so forth. So I was very lucky, supported early on by the NSF and other people. Now, sometimes it's very hard for young people to get enough support for their work. So the answer is money, support for your work, and money plays a huge role in success. And so you have to find a way to get support for your work. And this is one of the difficult things now that relates to the tenure system, is young people who come in and can't get enough support for their work are at a great disadvantage in getting research done. So it plays a huge role. And that's a system that has flaws in it. We normally in the U.S. now, when people start, they get what's known as startup packages of a lot of money. So then the other side of the, I think you can overdo the money thing to the point where it's actually detrimental to the success of a person, because you spend all your time figuring out how you're going to spend money rather than doing research. When I started, there were no startup funds. Columbia, although they gave me a job, my startup was zero, except they did give me full use of the stock room and a bunch of old bits of equipment that I could fix up with the help of staff. And so I feel lucky that I didn't have to have that, but I did get support from the National Science Foundation. But it can be overdone, but it plays a big role. The answer is it plays a big role.
Thank you, Harry. I will like to actually conclude the interaction, but Sanskriti has an announcement after that. So I just want to say to everyone here, it's been a great evening for us here. that Professor Gray actually graced us.
And a good morning for me.
And a good morning for you on a Sunday.
I have to tell you, JD, my coffee was very cold. I went by Starbucks on the way in and got a nice coffee, which is sitting over here. I can show you.
It's all cold.
but now it's completely cold. I'm going to replace it with water.
Okay. Yeah. So I would like to tell on behalf of everyone that Harry, we were absolutely grateful and we absolutely appreciate the time that you took and talked to us. And some things that Zooms are not good for is just being personal to you. But some things that Zoom is really good is that you didn't have to travel. You actually were sitting in your and you could see us to some extent.
Yeah, that's right.
And we could, and we could feel the love. So thank you, Harry. As you've done this for so long, you've been such a great mentor to your own students, but also students from other parts of the world who have just gotten a 5-minute chance to talk to you. So we remember every moment. And
now you're all part of what we call the Gray Nation.
Yes. Yes. Thank you.
You're all now full members of the Gray Nation.
The Gray Nation. Thank you. We the Gray Army, right? The Gray Army.
That's right. Okay.
Thank you, Harry.
Bye, everybody.
And Sanskruti has a announcement. Sanskruti.
Okay.
Yeah.
And next week we'll be hosting Professor Siddhartha Mishra next Sunday, and he will be talking about applications of partial differential equations and their numerical solutions to developmental biology and geophysics, modeling tsunamis. So so we are hoping to see you there.
Yeah.
Yes.
Thank you.
Before everybody leaves, we want a photo.
Photograph. Yes, we should have a photograph. Yeah.
Okay.
Please switch your videos on if it's possible. You just get a chance to get a picture with
somebody has to photograph the screen. Get a
screenshot. Yes, please switch on your videos.
Okay.
Kevin Vardhaman.
Kevin Vardhaman, Atif. Anyone of you or Vishal?
Yes.
Guys, please do that.
Send me the screenshot, okay?
People are still turning the video on.
Yes. Okay.
Send me the screenshot.
Yes, absolutely, Harry. We will do that.
Okay. Okay, great.
Let's have we done the screenshot, 𝗤𝗄𝗄?
Yeah, Vardhaman is saying yes.
We did it. Can we do one more?
Yeah.
Is there anyone else coming?
Anyone else who want to turn up their videos, please do it as soon as possible.
Please do turn on your video. Yeah. Thank you, Harry. Thank you very much. This was great.
Thank you, guys. All right.
Yeah. And I will write to you separately via email. Yeah.
Thank you.
Bye, everybody.
Bye.
Thank you, JD.
Yeah. Thank you, Harry.
Bye, sir.
Awesome.
Okay, guys, that was fantastic.
That was lovely.
Yeah. It was a great session. I hope you guys had a good chance. There are many questions, I'm sure. I'm sorry I couldn't take all of them, but I think he covered a lot of ground, as he said. So, and all the best for the future meetings as well. Okay, guys,
Yes,
take
sir.
care.
Thank you. Yes.
Thank you, sir. Thank you so much.
Thank you.